what we'll end up doing is taking a look at a reaction. And this is an important skill, just the part in black at this point. It is important for organic chemistry as well as general chemistry. So what you would do is look at your reaction and say, what things happened? What changed? So if we look at that reaction, we've broken some bonds and we've made some bonds. The bonds that we've broken, we broke one carbon-hydrogen bond. Not 4, not 3, only 1. How do you know it's only 1? You started with CH4, you end with CH3. Okay, so only one carbon-hydrogen bond is broken. After that, we broke one chlorine-chlorine bond. Okay. As far as the bonds that were formed, we formed one carbon-chlorine bond, and we formed one hydrogen-chlorine bond. Using the bond dissociation energies, we can then tabulate or use values for the energies required to break those bonds, because that's what the dissociation energy is breaking. So when we look at our broken bonds, well, that's exactly what the enthalpy or our tables is telling us, the energy required to break the bond. But if we look at our formed bonds, we're still only evaluating our bond dissociation energy, the energy required to break it. So what is that necessarily going to mean it's going to happen to your energy to form a bond? It's going to be the opposite. Okay? So really all you have to do is add everything up. The energy of your bonds broken, the energy of your bonds formed. Okay? You just have to take into consideration that you're doing the reverse, so you have to change the sign for your bond dissociation energies for the ones formed. That concept is apparently way too difficult to explain. And so what we say instead is you take the sum of the bond dissociation energies for broken, and you subtract the bond dissociation energies for those formed. Whoops, where did my minus sign go? My minus sign disappeared. There's a minus sign that should be right in there. So we end up telling you this formula. The formula is nonsense. All you're doing is just adding energies up. You just have to realize that the energy value you're reported or you're given only references the broken bonds. So you just have to change the sign on the formed bonds, and you now have your answer. You just add everything up. Okay. If you look at how our equation is set up and solved, and they go through and they take the sum of the energies of the bonds broken. Okay, so we took all those energies, and then they say, well, it's subtracting the sum of the energies of the bonds formed. Nonsense. It's not subtracting the energy of the bonds formed. It's subtracting the energy of the bond dissociation energy for the ones that were formed. Why don't you just realize that the opposite of formation, or the opposite of breaking, is formation. So if I need to change the energy of breaking, what should I do? Change the sign. It's not subtraction. I'm just changing the sign on that energy, which then means I just add all the terms together. One of those terms, or two of those terms, happen to be negative. Okay. They just decided it was easier to say, let's memorize this formula. It's complete crap. Okay. Yeah.
Sorry.
Okay. So what we would do is then just go through and plug in your terms into it, because that's the easiest way to present this. We can just tell you to memorize this formula and then plug in values instead of looking at the concept behind it. The concept is just adding the energies for each of those reactions. You just have to realize that the energy for the reaction is tabulated as the dissociation energy. If you look at a formation, it's the opposite of dissociation. The opposite of 328 kilojoules, in the case of our dissociation for our carbon-chlorine bond, is negative 328 kilojoules. Okay? So there's two approaches to going through and solving. Ultimately, they do the exact same thing. One is a conceptual approach, just add up the energies for each of your reactions. Okay? The other approach is, here's a formula. Take the bond associations of your bonds are broken minus the sum of the bond associations for your bonds formed. Either way, you get the exact same answer.
So in general, bonds that are broken take energy, and bond synthesis absorb energy.
synthesis releases energy. That's why it's a negative. Bonds that are broken absorb energy.
Okay.
Linda, yeah, that's why in the ice and salt lab, the water temperatures, the water and salt still went down because the energy was
Yeah,
absorbed.
okay.
Okay? Questions on this? Now's the time to ask it. Yeah, because you have a quiz on the last two questions are this. So. Okay. I think I heard somebody say maybe something reference, how do you know those numbers? Yeah. Those numbers are given to you. They're in a table. That's how you know those numbers. Okay. Okay. You just have to make sure you put them in the appropriate fashion. If we change the reaction, I can be creative here, right? Let's see what I can do. I'm horribly uncreative on the spot, so I apologize. Okay, so we don't have numbers here, but what we do have is summarizing what changed. So what things changed in the course of this reaction? What was broken? Okay. I have an oxygen-oxygen bond broken. So I can look up the energy for the oxygen-oxygen bond, and I come up with some random number. Okay, what else was broken? We also broke some hydrogen-hydrogen bonds. Okay, yes, I know it says H2 in the reactant and H2 in the product, but remember, that's not how the atoms are connected. Okay, H2O is really H bonded to oxygen bonded to hydrogen, right? Yeah. Right. Did I really just break one hydrogen-hydrogen bond? Two. I broke two of them. So I have to account for that in the breaking of my bonds, because that's what the equation is telling me. How can I account for that? Well, I could add another hydrogen-hydrogen bond broken, or I can just multiply that by 2. Okay? So this is where you would bring in that coefficient, because our equation is telling us that we need 2 of those to happen. That's when we bring in the multiple bonds breaking. What happens for our bonds formed? We formed an oxygen-hydrogen bond. This, unfortunately, was a little bit trickier than I'd hoped. Sorry.
Well, yeah.
How many oxygen-hydrogen bonds did we form to make one water molecule? 2. How many water molecules did we make?
2.
Okay. Does that make sense? Yeah. At this point, now what you'd have to do is go through and look up what those numbers are. Okay. So your broken bond, I have no idea. Let's pick a number, 42 kilojoules. Okay. For your oxygen-oxygen. For your hydrogen, okay. The hydrogen bond, 32 kilojoules. But there were 2 of them, so I need to multiply that number by 2. Okay. The bond formed. Well, I'd look up my OH bond, and what I would be looking up is, again, the dissociation energy. So the dissociation energy for the OH bond is 52. Super creative here. But that's the dissociation energy. This is the bond forming. It needs to be the opposite. What's the opposite of positive 52? Negative 52. How many times or how many of those bonds did I make?
4.
And I can add it all up. Okay. Why can I add it all up? The minus sign that we told you in that stupid formula is to take into consideration that you're doing the opposite. You're forming a bond. Okay. If we go through and look at it the way you're trained how to do it for some unknown freaking reason, we would go through and we'd say 42 kilojoules plus our 2 times 32 kilojoules. We would do that quantity minus the quantity 4 times negative 52 kilojoules. Whoops, not negative, positive. The result is exactly the same, except one involves a conceptual approach to what you are actually doing. You're just adding energies to each other. The other one says, we don't trust you to understand anything about concepts, memorize this formula. Take your pick.
So anytime things on the product side, you're forming that, so you're saying no matter what's the sign on the product side?
Why, and it's not quite no matter what. Okay. What is the energy that you got? It's 52 kilojoules was the number. What was that energy for? The dissociation of a bond. In this case, we want it to be a formation, so I have to make it negative because it is the opposite. Does that make sense?
So could you give an example of like dissociation would be like?
Your dissociation, if you look up the bond dissociation for OH, it is 52 kilojoules, positive 52, because you are breaking a bond by definition. What happened in this reaction? Did you break OH bonds? No. So you have to report the opposite of the breaking. So you change the sign.
So if it was the H2O on the reacting side yields, then the H2O.
You're going to have to switch everything around again. Yep.
Does this ever come for like the breaking of like double bonds?
Can we break double bonds?
Sure.
Sure. You just have to know the bond energy for breaking a double bond. Yeah. Which, now that I think about it, could become very relevant here in a second.
So dissociation could be putting together or pulling.
Dissociation is always pulling apart. Every single time, it is pulling apart.
Okay.
If you want that dissociation energy to represent a bond formation energy, what must you do?
Just change.
You change the sign. Now it's not dissociation energy anymore. Because changing the sign, you've reversed the reaction.
Dissociation, you just keep the signs?
The dissociation is always breaking a bond. And so because the table is listed as dissociation energies, there's no need to change it because it is the dissociation. Okay? So, part 2, on your quiz. Pull out a sheet of paper. Yeah, I'm actually a little nervous on this one. I don't know when it is actually. It's either Monday or Wednesday.
We don't have school.
So then that, my notes say you have a quiz, not a test. So I don't know. That's all she told me was that there was a quiz
On Monday?
on Monday on modeling. So I don't know what that means. So if the schedule says test, you should be preparing for a test. If your schedule says test, you should be preparing for a test. All I've got are quick notes that say there's supposed to be a quiz on Monday. That's all my quick notes say. That what we are talking about today is modeling, and in modeling you should be ready to answer questions on a quiz. I have no idea what that means. Right? So, I'm going to time you now because it's what I was told. You get a minute to talk to each other about this quiz question. Can't write anything. Yeah. Which of the following will have the largest lattice energy? Your zinc or sulfide will have the largest lattice energy. Why? Biggest charge. Right? So the two things that contribute to lattice energy are the size of your charges and then the size of the atoms. The charge trumps. Zinc has a +2. Sulfur has a -2. Those have the largest charges. That compound is going to have the largest lattice energy. If we go through and look at the next one, this one actually explains a little bit nicer. We've got the size of the ions and the charge. Charge trumps, so magnesium chloride is going to be the largest lattice energy. When we then move to lithium chloride versus sodium chloride, lithium is smaller than sodium, increases the lattice energy, so it is higher than our sodium chloride. As the number of bonds between two atoms increases, the distance between the atoms decreases. You're putting more electrons in between that space. That's going to draw the atoms closer to each other. Which is the same question here. Which of these is going to be the shortest? You're putting more electrons between those two carbons in the triple bond. Those two atoms get drawn closer towards each other. This is a fun one. Based on the electronegativities of the atoms, which of the following bonds would you predict to be the most polar? How many of you guessed this answer? Carbon bromine. How many of you guessed the carbon nitrogen triple bond? I guessed the carbon nitrogen triple bond. How many of you guessed number 3, the carbon silicon bond? Nobody. Fascinating. Guess which one has the largest difference? Take a look at your electronegativities. The carbon silicon bond has a difference of 0.6. Carbon bromine has a difference of 0.3. And nitrogen has a difference of 0.5. Fascinating. That is a question that you should bring up with Dr. Wood.
So she
Yeah.
got it wrong.
So-
I'm supposed to know those numbers.
So yes, this is one of the issues that becomes tricky with electronegativities. So this is why you should ask her to clarify that situation. So if you go off of general trends, the answer is number 2, period. Okay? If you go off of strict electronegativities, the answer is 3. At no point should the answer be the carbon-bromine bond. Okay? Unfortunately, I don't have anything else to tell you on that. It's going to come down to what she's expecting you to know and different approaches to this. One of the biggest discrepancies with this question comes from that term most polar. Okay? The polarity of the carbon-bromine bond is more polar than the carbon triple bond nitrogen, but not because of electronegativities. Okay? That's where you run into the issue. So if you go based strictly off the electronegativities as the question suggests, it's actually the carbon-silicon bond. Which if you look at the polarity of molecules, it's not the carbon-silicon bond. Okay? So I'm going to highlight that as an issue when I send her notes of what happened within the class. You guys should also ask for clarification on what she expects out of that question. Okay?
Just a quick question. So if we're just going most polar, then the carbon-bromine bond is most polar because, finish that sentence for me.
It has to do with the difference in the charges, so your electronegativities, and the distance of the bond. So I'm pretty sure that came up in the lattice energy section, which this isn't technically lattice energies because it's not an ionic bond. But you end up going back to that same general formula where it's the difference in your charges versus the distance, the length. Which is predicted to have the longest carbon-oxygen bonds. I real quickly picked a Lewis structure thing that I happen to have handy. So I've got the carbonate one drawn up there. If we look at carbon dioxide, our best Lewis structure for carbon dioxide has double bonds. Our best structure for carbon monoxide has a triple bond. Okay, the one that's going to be the longest is the one where, on average, we're closer to single bonds. Okay. Your carbonate, due to that resonance structure, all of those bonds are going to be shorter than a double bond, or sorry, longer than a double bond, but shorter than a single bond. Why would they be shorter than a single bond? They have some double bond character in all of them because of the resonance. Okay? As we're going through these, if you got a question, just stop me. Electron configuration is most consistent with cobalt. That's what it is. Electron configuration for iron +3 is which of the following? You go to your 3D5. What?
Can we go back to the other?
Sorry.
Real quick.
Did I not look at it? I didn't look at it very carefully.
3D.
1, 2, 3, 4, 5, 6, 7. That says cobalt, yeah.
Okay.
Iron +3. It'll lose 2 electrons from the S first. It's 4s2, and then it'll lose 1 electron from the D. Now, there's lots of talking here. I'm just trying to figure out what's going on. Is there a question?
Why is the S lower?
Wait.
Because it's the outer.
Too many questions.
It's in the fourth.
So your S, yeah, you always go from the highest energy, which is your S. So it'll be your 4s.
So you go from the highest orbital with the most complex, or is it the most complex design? I don't know what that was, patterns.
I really don't, believe it or not, want to get into it because you'll see it in question 11 that I think is weird too.
Oh, okay, sweet.
Which of the following best describes the boron-chlorine bond? This is based off of electronegativities. Your ionic bonds are a metal and a nonmetal. Boron and chlorine are both nonmetals. Nonpolar covalent is only the case when you have the same atom attached to the same atom or carbon to hydrogen as a general trend. This doesn't fit either of those two categories, so it's got to be polar covalent. Yes. Carbon to hydrogen is classified as nonpolar covalent. Yes. Strictly, how do you determine each of those categories? It's the difference in electronegativity. Why is that a bit obnoxious then of a question? How many of you know the electronegativities for boron or chlorine? Yeah. So you need some kind of rule of thumb to come off of it. So ionic bonds, metal, nonmetal. Always. Not always, but they will be ionic. Okay. Nonpolar covalent, anything bound to the same type of element, because then the difference in electronegativity will be 0. By definition, nonpolar. The one extra caveat on the nonpolar covalent as a rule of thumb, carbon to hydrogen is classified as nonpolar covalent. What's classified as polar covalent? Anything that wasn't ionic, anything that's not nonpolar covalent. Okay. It strictly comes down to a difference in electronegativity, so you can see some gray areas between those ranges by looking at the differences in electronegativity. Which element is a +1 ion for the electron configuration of krypton 48? It's the one in black. I don't know why I did that, but it's the one in black. Rhodium. If anybody can come up with an explanation for that one that makes sense to me, I would love to hear that.
I know one.
Because
I know one.
She said there's, you go over 8 to PT, you lost an electron, so you go 1 to the left.
that is rhodium's electron configuration, 5s1-48. That's its electron configuration. You remove 1 electron from it, that's going to give you rhodium as your +1. Why does rhodium have a 5s1-48?
So she just forgot to put it in.
She's forgetting a lot.
No, this isn't a forget thing. The configuration for rhodium is 5s1-48. If you make that a +1 cation,
You have to take off
it's
the light.
48. You take off an electron, it's 48. How did you get rhodium to be 5s1-48?
Oh, this makes sense because the 5s. How did you skip one atom?
Why did you skip an electron in the 5s orbital? This is the electron configuration for rhodium, 5s1-48. Its ground state form, 5s1-48. You remove a single electron, it comes from the 5s. Why does rhodium have a 5s1-48? This is a perfectly honest question. I don't have a good answer for this. I was curious if you guys knew.
247.
Because it's not.
Oh, okay.
Yeah.
Because it'd be 5s.
Okay, so if that's confusing you, ignore it because it is a confusing ion. So I was hoping you guys had an answer for that. If you don't have an answer for it, I'd probably just kind of ignore it and move on. That is the electron configuration for rhodium, 5s148. That is the electron configuration, period. So,
That's why it's 4d8.
so why did one of the electrons move into the 4d orbital? That's the real question.
That's the better.
And good question. I have no idea why. But that's its configuration.
Is that something I'm going to have to know?
Okay. How many resonance structures can be drawn for nitrate? You get 3. Do you need me to draw all 3? Thank you. I'm going to accept that and move on really quickly because I don't want to draw them all. A molecule of CS2 contains 2 double bonds. I heard a bunch of people talking about triple bonds. We actually addressed the issue on this when we looked at this. Whoops. That is a resonance structure for CS2, where it has 1 triple bond and 1 single bond. This is not a good resonance structure because the sulfur on the left carries a -1 charge, sulfur on the right carries a +1 charge. If you made it symmetric, double bond on each side, you lose the charges. Okay. Using the table of bond association energies, you might need to apologize, or I need to apologize here because I screwed up the calculation real quickly when I did it this morning. Bonds broken, you broke the carbon-carbon double bond, which came in at 614 kilojoules. You broke the hydrogen-chlorine bond, which came in at, where'd it go? 431. Okay. You formed a carbon-hydrogen bond at 413. You form a carbon-chlorine bond at 328. And you form the carbon-carbon single bond at 348.
So that needs to be on it too?
That needs to be there.
Okay, cool. Can I write this down?
Yep. The format that I drew out here is your standard formula format. Products or reactants minus products, in this case for your dissociation energies. Okay, we'll go 1, 2. Yeah.
Why can't you just break the 1 single bond and then just keep it as?
It's a good question. Take a look at the difference in energy between a carbon-carbon single bond and a carbon-carbon double bond.
It's not half.
It's not half. By breaking the double bond, just the double bond, it's not 348 kilojoules. It's actually, what is it, 250 something kilojoules? Okay? And that's because when you look at a double bond, it's not 2 single bonds. One is a single bond and the other one, or a sigma bond, and one is a pi bond. Pi bonds have different energy than sigma bonds. They aren't referencing the energy of the pi bond here, they're referencing the energy of both bonds together. Just a sec.
That was my question.
What is a sigma and a pi? This comes from hybridization theory, which I don't know if you guys talk about, you should talk about, but I don't know if it's actually stayed in the curriculum for 151.
I think it will because it's in the molecular packet.
It is? Okay.
Talks about hybridization.
Then you'll see hybridization. Well, we might attempt to talk about it today. So that number is wrong because I didn't take into account the carbon-carbon single bond. Calculate your delta H for the last one. Broken. You broke 6 nitrogen-chlorine bonds. Okay. Which gets you that 200. 6 times 200. Subtract the energy of the bonds formed. You formed 1 nitrogen-nitrogen triple bond at 941. And you formed 3 chlorine-chlorine bonds at 242. Okay? Put it all together and you should get the answer of, I think it was -4. Oh, actually, there it is. Negative. Okay? Questions? Okay. So what we're going to move into now is modeling. Okay, I do find your textbook's organization on this to be a bit odd, because you should be talking about modeling when you talk about Lewis structures at the same time. Because to figure out modeling, it's based on the bonds within the structure. If you don't know the Lewis structure, you can't predict the model. Okay? So the shape determines a lot about the reactivity of an individual molecule. So we have to understand a little bit more about shape. Okay? To determine the shape, you will need to note the difference of the bonding and non-bonding electron pairs within your Lewis structure. So you have to have a Lewis structure. If you don't have a Lewis structure, you can't answer any questions about shape. So we've got the rule set I dropped back up there because I just thought it would be important to go through and do. Okay. If we simplified this out and picked, say, one of these molecules, let's pick the carbonate. We're all super familiar with that Lewis structure now.
Super.
Come on now. There it goes. If I want to predict something about, whoops. Sorry, you'll understand why I drew it a little screwy in a second. When we go through to draw our Lewis structure, we pick our center atom, and remember one of the things that I suggested that happened with Lewis is that Lewis was based off of cubes. That's how he designed his theory. Okay, so when we put our oxygen atoms around, we're putting the oxygens on a face of the square of our center atom. So this is where modeling is going to come in handy, is looking at that center atom. That carbon is our center atom. So what we now need to do is identify what the textbook references as electron domains. Okay. Ignore the electron part and look at a domain. How many domains are around our center atom?
3.
I did not say electron domains, I just said domains.
Oh.
There are 4 domains. 1 for each face of the square. So take a look at this domain. Are there any electrons there? No. Take a look at the next face of the domain. That sounded weird. But are there electrons there?
Yes.
The next domain. Are there electrons there? The next domain. Are there electrons there? How many electron domains are there? 3. Questions about that? I think you're full of crap. I'm sure there's questions on that. Why are there not 4 domains? There's 4 bonds.
Only 3 sides of the.
Good. Focus on the sides of the square. That's it. Okay. One of those domains happens to have more electrons than the other domains. Irrelevant. Are there electrons in that domain? Yes. Count it as a domain, move on. Okay. There could be 50 billion electrons on one of those faces. That's still one domain. Okay? So in this case, we say 3 electron domains around our center atom. So let's pull up a more difficult example here. How many electron domains now? For the one in the lower left-hand corner. What was that question? It's a really important question. What is your center atom? If you don't have a center atom, a clear center atom, how do you answer the question? You don't. That's how you answer the question. Okay. So what if I tell you your center atom is now carbon?
2.
Draw your box around your center atom. Look at the domain. Are there electrons on that bottom domain? How about the top? Right? Left. So for the carbon, there are 2 electron domains. What if instead of asking about carbon, I asked oxygen?
4.
4.
Yes, 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 yes. There are 4 electron domains. Okay, when we're looking at our domains, there is no difference between bonding and non-bonding. It's are there electrons there? Yes, that counts. Yes.
Kind of going backwards, but why would you have hydrogen attached to the carbon if the carbon is a center atom?
Remember that there are some structures that you are not predicted to know the center atom because there's no clear rule on why it would be the center atom. We can run into arguments all day long about how you could potentially come up with the proper Lewis structure for this formula. Ultimately, you should be given it at this stage in the game. Okay? So you now know electron domains. So that actually defeats the purpose of the next slide, which is referencing the electron domains on an individual shape. Okay? You'll notice that your textbook is going to reference your center atom as A, and then the other atoms as B. Okay? So we just look at our electron domains. The electron domains on A would be, in this case, 4. Even though we have 10 electrons around it. Doesn't matter. How many electron domains are there? There's only 4. Please reconnect. Okay. Oh, come on. Get to the next slide already. So the reason this ends up coming up is this concept of what's happening with methane, CH4. If we drew out the Lewis structure for CH4, you should all predict this Lewis structure, right? Okay. Are the hydrogens different from each other? No. So we would expect those hydrogens to get as far away from each other as possible. Because if those atoms get near each other, you'll get that positive nucleus-nucleus repulsion. So we would expect each of those bonds to be exactly the same distance from every other bond within the structure. So let's test that. What's the bond angle in that upper right-hand corner? How about the left? And the lower left? And the lower right? 90. And we're all saying, perfect, this matches exactly what it is. And we already heard a suggestion here coming out at square planar. There is one bond angle you did not reference, or sorry, I did not reference yet. What is the bond angle between those hydrogens? 180. Are all of these bonds equally distant away from each other? No. Lewis structure fails at representing the proper electron origins. Ultimately, why? Lewis structures are drawn where? On paper, which is two-dimensional. A molecule is three-dimensional. So what we are trying to do with these shapes is use the Lewis structure to interpret something about the electron domains, and then what we do is classify those electron domains into particular shapes. Someone came down and said that this shape is this. Okay? So if we pick, say, carbon for this case, we have how many electron domains? 4. So what we can do is take each of those 4 domains and turn them into a balloon, which is supposed to represent the electron cloud. If we try to force them all into the same plane here, what happens when I remove my ends? In fact, I have to poke it a little bit. The balloons aren't big enough. If I shake it, are they now all in the same plane?
No.
No, they've actually shifted out of the plane. Lewis structure says, son of a... Lewis structure draws it as all in the same plane, right? Okay. All we got to do is take the atom and say, give it some energy. How do we give it energy? Heat it up. Energy. Are those now all in the same plane? No. Someone looked at this and said, what shape is this? Any Dungeons and Dragons fans? It is the 4-sided dice. It is a tetrahedron. Okay. Because of that, we now refer to it as a tetrahedral shape. You were all phenomenally good at coming up with that shape name, right? Good job. Okay. Which means ultimately you have to have it memorized. Someone came through and said, this is what we call it. When I reference the element that has 6 protons, you tell me that element is? Why is it called carbon?
Because it's just there.
We looked at it and go, whoa, carbon, that's its name. Everybody just sees a black lump of something and says, oh, that's carbon. Even if I showed you something with 6 protons, you say, oh, that's carbon. Why is it called carbon? Old, dead, white guys. Why do we call this a tetrahedron? Old, dead, white guys. Right? You are responsible for knowing it by that name. You have to follow the rule sets on identifying the electron groups to say this is what's going on within it. Okay? This electron group theory is known as valence shell. Why valence shell? We're looking at the outermost electrons. Valence shell electron pair, ultimately our bonds, repelling each other. Often referred to as the Vesper model. Did I name it differently?
Yeah, well, because here it says VES. I think it's okay if you just switch the electron and
Valence,
shell.
yeah.
I don't think that makes a big difference.
It's valence shell electron pair repulsion theory. I'm right. Okay. We run into this concept of electron geometry and molecular geometry. So far, when we looked at methane, we came up and said it was a tetrahedral shape. Okay? So to determine our electron geometries, all we got to go through and do, kind of ignore that middle part because I goofed somewhere up at the top. Just do that. Is we would look at the electron groups, or the electron domains around our center atom, and we'd say, how many do we have? Well, if I have one group of electrons around my center atom, by definition, the shape will be a straight line. It's a linear shape. There is no other option. If I have 2 groups of electrons, okay, so if we pick a center atom, and I now draw in atom B, 2 groups of electrons, remember, those electron groups want to get as far away from each other as possible. As far away from each other as possible is a straight line. Okay? Don't give me this stuff that, yeah, you could draw it like this. That is absolutely true. You could draw it like that. And Lewis structure says you can draw it like that. Valence shell electron pair repulsion theory says that those 2 groups of electrons need to get as far away from each other as possible. Are they as far away from each other as possible in this drawing? No. So what we could do is, if we drew our Lewis structure this way, look at our electron domains and say, I drew it wrong. Let me redraw it to better represent the actual molecule. Okay? 3 groups of electrons. Just a sec. You'll end up with another shape, trigonal planar. The way that those 3 groups get away from each other as far as possible ends up being in a trigonal plane. So we have trigonal because it is 3 points. And if I tried to get those balloons as far away from each other, even if I shake it, where are they? All in the same plane. So it's trigonal planar. Yeah?
Where does bent fit into the 2 electron groups?
It does not fit into the electron geometry. So don't worry about it. If we add a 4th group of electrons, we already looked at this one, and I can't hold it quite right. Okay, we end up with, as I shake it, that tetrahedral shape. So you're responsible for knowing 4 groups of electrons being tetrahedral, or 4 electron domains. Okay. What happens if we add a 5th balloon? Well, I don't have a 5th balloon, so I can't show you. But we end up calling a new shape trigonal bipyramidal. Because we get 3 atoms in the same plane, 1 atom above, there's our tetrahedron, and 1 atom below. So it is bipyramidal, because there's a pyramid up and there's a pyramid down. The last one, if we have 6 electron domains, it's referred to as octahedral. Any questions about those last 2?
Octa? Isn't that 8?
Let's pick PCl5. We draw our box around it, put our chlorines on it. Those are chlorines. That's 4 chlorines. I've covered each of my faces. But I have a 5th chlorine.
What is the cube you have 2 more?
3-dimensional shapes. Where's that 5th chlorine going?
Or down?
What we're looking at is not a square, but in actuality a cube. And a cube has 6 faces. So I can draw my chlorine, my fifth chlorine, kind of coming out of the board at you on that fifth face. When I then go through and draw in my Lewis structure, I would end up with 5 electron domains. I'm responsible for knowing that 5 electron domains is trigonal bipyramidal. Have I exceeded the octet? Absolutely. Am I allowed to exceed the octet? Clearly I am, because we made that molecule. Okay. Why am I allowed to make that molecule? Because phosphorus is in that third energy level. It can expand its octet. We move to the next one. 6 electron domains, SF6. Okay. How do I fit 6 things around a cube? You use the other side, so it's now going behind the cube. So imagine just a die. Everybody's seen a die, right? It's got 6 faces. That's what we're looking at when we're trying to draw these structures. But you were trying to draw something in 3 dimensions on a 2-dimensional piece of paper. You will suck at it. That's okay. Accept it, count your domains, classify the name. Okay?
Real quick.
Yep.
Sometimes when you draw that, you see like a hashtag line and a little triangle.
Right.
Which one means into the paper?
One of the attempts that your textbook will try and do, and you'll do more in organic chemistry, is if we take a look at the tetrahedral shape, you'll notice that there's 2 solid lines. Those solid lines imply that they are in the plane of the board. You'll notice that this one is wedged and the other one is dashed. Okay? The wedged is getting bigger. What happens when something gets bigger? It looks like it gets a lot bigger. I was not going to kiss him. Come on. As we get closer, things get bigger. That's what our wedge is trying to show. As things get further away, they start to become kind of mirage-y shape, and we start to see weird kind of dotted lines. That's what's happening with those wedges and dashes. That is our artistic rendering of 3-dimensional shapes. Okay? So, we've now established that we can get an electron domain. How do we get our molecular geometry? Okay, well, some smart aleck went through and said, okay, let's take a look at the Lewis structure for ammonia, NH3. And you guys should be awesome at drawing NH3 at this point. There's the Lewis structure for NH3. How many electron domains does it have? 4. How many electron domains did methane have? 4. So the shape that we would get, tetrahedral. But in that assumption, when we got tetrahedral for methane, is we said all 4 hydrogens were identical to each other. All 4 electron domains were exactly the same. Is that the case?
No.
No. I'm showing a line versus dots. Very clearly, they're different. Okay? How does that difference manifest? That's when we come into molecular geometry. So in molecular geometry, I don't necessarily care per se about the electron domains. I care where the atoms are located relative to each other. So what I end up doing is taking a look at my tetrahedral geometry. The balloons are too far away. And I say that one of those groups is non-bonding, and 3 of those groups are bonding. Okay? I'm still going to be forced in that general tetrahedral shape, so I can't now make it trigonal planar. Okay? But it's not officially tetrahedral, because I don't have a 4th atom for my tetrahedron. What have I just created? A pyramid. A trigonal pyramid. Trigonal pyramidal. Okay, or pyramidal, I don't care how you pronounce it. Okay. That change in shape, and ultimately the name that we associated with it, came from some old dead white guy. Okay. You're responsible for knowing that shape and coming to that conclusion. Okay. So that when we look at each of our electron geometries, we now have to evaluate each of those groups and say, are they all the same? If they are all the same, then the shape is exactly what it is. The electron geometry is correct because they are all the same. But what happens if it is not all the same? if we go through and take a look at the trigonal planar situation, if one of those groups is no longer an atom, no longer a bond, now when I look at the atoms aren't in a straight line anymore, they are bent. Okay. If I move to the tetrahedral shape, we already talked about this. For our ammonia, it's trigonal pyramidal. It's pyramidal instead of planar because that group of electrons, that lone pair of electrons, is pushing down and keeping the other three atoms from achieving the plane. What happens when I move to now two non-bonding pairs of electrons? They're still occupying space, so the other two atoms can't straighten out. They are forced into a bent shape. You'll notice bent shows up in a bunch of different places. Okay? It doesn't have to come from the same origin, it's just the same name that we're associating with it. You'll notice that as we move down in our electron groups, the amount of possible shapes that come out of this becomes increasingly more prevalent. Sucks for you. You're responsible for knowing all of those. Okay? And the names. Because if I ask a test question, you have a structure that has 5 groups of electrons, 3 of them are bonding, 2 of them are non-bonding. You have to be able to tell me it's T-shaped. Okay? Because that is the name that we have decided to give to it. And before you panic and go, oh, that's way too hard, I could never do that. What was that element with 6 protons again? How do you know it was carbon? Because you spent the time to memorize it. You're doing the same thing here. Okay? You've already succeeded at figuring out carbon. You will succeed at memorizing these. Okay? Yes?
This is kind of a stupid question, but why aren't they spherical?
What do you mean spherical?
Like the shapes, because if you include motion, wouldn't they all be like...
So they would all be constantly moving, and you're right. They are all constantly moving. But if I take this atom and start to move it down, what do these all do? Start moving away from it, right? On that spherical shape. So as this comes down, where does this one go? Up to give you a linear shape. It's still the same shape. Right. So yes, these are constantly moving, and we could evaluate that. It's not worth the trouble. Freeze it, evaluate it in that shape. Okay. This is what I would highly encourage you to memorize, all the way up through tetrahedral. This is a nice little table that I put together. If you take a look at the tutoring center, they've put together a similar sheet, but they've gone through and added the trigonal, what's that last one called? Octahedral. Trigonal bipyramidal and octahedral. They've included those names in their chart. Why did they include it and I didn't? I'm an organic chemist. I can only count to 4. Okay? So all of my focus is stuck with these. The trigonal bipyramidal and the octahedral are technically inorganic chemistry. We don't see those in organic chemistry, so I don't care about those shapes. Okay? They tend to show up a little bit less frequently on exams because there's no need to test on them because you see them much less frequently. Okay? So realize you are responsible for those. These ones, you're going to have to know. Okay? You will absolutely see these. The other ones are kind of random spot checks. Did you advance your knowledge further? Okay? So in reading this, find your electron groups. If you say it's 3 electron groups or electron domains, we move to trigonal planar for the electron geometry. We then take a closer look at our Lewis structure and say, of those 3 electron domains, 2 of them are bonding, 1 of them is non-bonding. Well, 2 bonding, 1 non-bonding means bent shape. Okay. I would actually encourage you to go through when it comes to shapes and do the trigonal bipyramidal and the octahedral in this fashion on your own without using the test or the tutoring centers. Okay? Because that'll help you start to pick up those patterns and figure out those shapes and names associated with them. Questions about that?
It's dumb, but I'm going to say it. She gives us a little 3x5 card in the test.
Oh, that's right. I didn't know that.
I mean, we could write that on there. Would we always have this as a reference? Or if we're going into organic, you want us to memorize this, it's just better.
If you're going into organic, you should have these ones memorized. So what I would do as far as your 3x5 goes, I would memorize these, the 3x5. I would put the bipyramidal and the octahedral on it. Particularly if there were shapes that you're like, I have no idea why they call that, like, for instance, I have no idea why they call this the sawhorse. Does that look like a sawhorse to you? Anybody seen a sawhorse? If you turn it on its side, yeah, it does look like a sawhorse. There's the fulcrum, and there's your kind of lever arms on either end of it. Okay. If you can't see it, if you don't know where the name is coming from, it's probably a good idea to write it down because you won't be able to consistently find it. Okay? Non-bonding pairs and bond angle. Okay, this is probably the last big concept within this. If we take a look at tetrahedral geometries, methane, ammonia, water all have tetrahedral electron domains because they all have 4 groups of electrons. So they are all in that tetrahedral electron domain geometry. Molecular geometry, methane is tetrahedral. Ammonia is trigonal pyramidal. Water is bent. One of the things that we might predict, at least in methane, is the bond angles are all identical. They are. They are all 109.5. What happens as I move to ammonia? Are all of those groups of electrons the same? No. That non-bonding group of electrons is different from a bond. Where are the non-bonding groups of electrons relative to your center atom in comparison to, say, a bonding group of electrons? Closer to the center atom. So what ends up happening to our shape? Well, fine, fish out the stupid worms. There's our tetrahedral shape. This, okay, there's our tetrahedral shape. Okay, ish. My hands weren't all in the way. Come on. So my hands are going to stay in the way. There's nothing I can do about it. We have our tetrahedral shape. These are all roughly down. All 109.5 degrees. If this group is held closer, what happens? To hold from the other end.
Oh, they become more and more planar.
Tetrahedron. Center of my knuckle is carbon, hydrogen, 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 and my wrist is hydrogen. What happens as my wrist gets closer to the center atom?
They become planar.
These electrons push down, which means where do these electrons go?
Upward.
They go upward towards it?
No, actually not down.
They're going to go down away from it. What happens to the bond angle between my fingers? It gets smaller. What happens to the bond angle when we move to trigonal pyramidal? We went from 109.5 to 107. If we add yet another non-bonding group of electrons, it's pushing even closer to the center atom. What happens? It gets even smaller. I thought it was 105.7. Okay. The rest of the slides in this talk ultimately go through the other electron domains, so you can see these pictures. I'm just kind of referencing them. You should have the context now to figure it out. We even talked about the larger molecules. I know, we're done. The larger molecules don't have a strict center atom, so you would have to specify what your center atom, what you're referencing, the shape on that atom, the shape on the next atom, the shape on the next atom. You'd have to specify for all of them. That's what this last slide is showing. Thank you for your